Hello everyone, I am Pawan Sharma. In this video, we are going to solve the questions based on aerospace structures from GATE 2007. In the given question number 2, a spring mass damper system is given, a spring with stiffness K, mass M, and the damping C, where the mass is given 1 kg and damping ratio, which is E, is given 0.2, and the natural frequency is also given to 5 radian per second. In the question, we have to find the damping of the system. We have to find C. Yes, the damping ratio is nothing but it is the ratio of the damping of the system and the critical damping. Critical damping is nothing but it is given by formula 2m omega n, where m is the mass, omega n is the natural frequency. So we can easily find the value of C. Cc multiplied by E. 2m omega n multiplied by E, which is nothing but 2 into 1 omega n is given 5 and 0.2. We will get the answer 2 Newton second per meter. This is the unit for the viscous damping. As in the question, we can find the answer by only checking the units only for this question. So answer A is correct. Now coming back to the concept. Here the value of E is given 0.2. The answer is here, but for extra knowledge, the damping ratio is given 0.2. What is the significance of this ratio? For example, if the system having the damping ratio equal to 1, we call this critical damped. System. And if E is greater than 1, then we call overdamped system. If E is less than 1, then we call underdamped. Okay. As in the given question, E is equal to 0.2. It means it is underdamping. For this, if the system having underdamped system, then for example this is X and this is T. For example, this is the mean position of any system. If we now displacing it from this position to some position, let's say X0, now we are releasing it from here. What it will do? It will goes into oscillation before coming to the rest. As amplitude is decaying because the damping is present in the system. But if the system is critically damped, then the system will not go into any oscillation. It will come quickly as possible to the rest. So what is the significance of the critically damped system? For example, this is the runway and this is the airplane or aircraft, and this is the landing gears. If the system is, as we know, the landing gear consists of the shock absorber. So if the shock absorber or say damping system present in the landing gear is not critically damped, then what will happen? It will come and then again jump. It will not come to the rest smoothly, which will definitely not be a good experience for the passengers. Hence, critically damped system is important. If the we know that when the aircraft lands, simply it smoothly land. There are some jerks and some disturbance, but not like this. So there comes the importance of any critically damped system. Question number 6. Here a continuous system is given. It means an elastic beam with cantilever boundary condition. It is a beam with cantilever boundary condition. One end fixed, other end is free. Here in the question it is asked the number of natural frequencies. As we know that the particle, every system or everything, every body is made up of particle, not considering the biological bodies, they are made up of cells. So here every solid body material are made up of particles. Here there are a particle can go upside and downward, backward and forward, and sideways movement. So a single particle consists of 3 degrees of freedom. Now we know that a continuous system is made up of several, or we can say countable infinite particle. We cannot say that infinite particle, but there is a particular number of particles which are actually countable infinite, we can say. So as infinite number of particles are there, then each particle perform they have their own 3 degrees of freedom. So we can say there are infinite number of natural frequency for a continuous system. And what is continuous and what is discrete system? We have seen that motorbike, this is a seat and somebody is sitting. These are wheel and these are the springs, shock absorbers, and in the advanced bicycles there are dampers also present in the. Here we can separately consider this system as like this is spring because of the shock absorber, and the damper and the mass of the rider and the other component of the motorbike. So we can here see the separately the damping, stiffness, mass, but in the case of any continuous system these things are dispersed, means these are the everywhere. If we take any scale, measuring scale, and we just give disturbance, it will come back to stationary position after some oscillation, because here there is a damping present itself in the system, and because of the air friction and drag there are damping present. So here we cannot separately distinguish where or we can say these are the damper and these are the stiffness. So these are the difference between a continuous system and discrete system. Problem number 13. The question says that it is a plane strain problem in xy plane. For example, this is the Cartesian coordinate x, y and z direction. In the question, plane strain means, what is the meaning of the plane strain? First we have to understand. It means that, for example, this is the some solid body, elastic body, which is subjected to the stresses, let's say sigma x, sigma y, and this is sigma z, or there may be shear stress also, tau x, y, tau yx tau xz tau zx. But the strain terms exx, strain in x direction, normal strain, eyy, strain in y direction, and ezz. These are the normal strain in x direction, y direction, and z direction. And the shear strain xy, yz, zx. And these are the strain which is shear strain terms, and these are the normal strain terms. In the plane strain problem, it means that the strain, let's say z direction, strain in any one of the direction is 0. Here xy plane is given, so the strain in the z direction will be equal to 0. And also shear strain in the z direction, there is no angular deformation in the z direction will be there. xz, shear strain, yz, they all be 0. Now we have to find the terms which are non-zero stresses. From the generalized Hooke's law equation, we know that EZZ 1 by E sigma ZZ minus Poisson's ratio bracket sigma XX plus sigma YY. E is the Young modulus or modulus of elasticity of that material. As the plane strain, EZZ should be 0. So by putting 0, nu is the Poisson's ratio, we will see that sigma z, normal stress in the z direction is equal to Poisson's ratio sigma xx plus sigma yy. So it means that sigma zz is not equal to 0. And sigma xx and sigma yy is also not equal to 0. So these stresses term will not be equal to 0. These are the normal stresses. Now we have to see whether the shear stress is 0 or not 0. As the shear strain in xz and yz direction are 0, we know that the shear strain is, these are the shear stress. For example, shear strain in xy plane is equal to shear stress in xy plane divided by g, which is the shear modulus. We know that the formula. Now sigma, shear strain in xz is equal to 0 by using this formula. Similarly, like xz equal to sigma xz divided by g. If this equal to 0, then sigma xz will also be 0. Similarly, shear strain in yz plane, shear stress in yz plane divided by g. If it is 0, then sigma yz will also be 0. So the terms of stresses which are non-zero is sigma xx, sigma yy, sigma zz, and sigma xy are not 0 or non-zero terms. These are the correct answer. Sigma yz and sigma xz will be 0. In the question number 14, we have to tell the number of independent elastic constant in an elastic anisotropic solid or the material. Before solving this problem, we talk about some different materials. For example, isotropic material. Isotropic material are those material in which the property in every direction is same. For example, if we stretch the material from this direction by some force of 10 Newton, let's say, it will stretch in the direction of the applied force and reduction in the transverse direction because of the Poisson's effect, Poisson's ratio or Poisson effect. Now, if we stretch the material in this direction by same force of 10 Newton, we will see it will stretch by same amount delta x, which is here, as the strain will be same if only if these dimensions, let's say this is L and this is also L. So there is a reduction in the transverse direction will be same and the elongation will also be the same. One more thing, in the isotropic material, the included angle, for example, if this is a square or rectangle, if the angle between them are 90 degree, after applying the force, it will remains 90 degree. There will be no shear strain like this. Okay, this is the basic of isotropic material. And also, if we are only applying the shear force, for example, on this surface, parallelly we are applying the forces parallel to this surface, there will be only shear strain. Means the angle between them will change, but there will be no elongation. Okay, this is the property of isotropic material. And the number of elastic constant, independent elastic constant in isotropic material are two, either E, G or nu. Any two can be used to find all other. Now coming back to the question, anisotropic material. Anisotropic material are those material in which the property of the material are different in different directions. For example, let's say this is X or this is Y. Then if we are considering any property, let's say elastic modulus, Ex will not be equal to Ey, elastic modulus. Similar, Gx shear modulus will not be equal to shear modulus in y direction. Okay, and also let's give the answer. In the anisotropic material, there are 21 independent elastic constant that is required. Okay, now giving some other property, like for example, if this is an isotropic material and we are applying the force, it will not only elongate, but it may show a different behavior than the isotropic material compared to isotropic material. Like it may undergoes into shear also. There are different behavior. Okay, by applying the force, there may be shear or bending can be possible. Question number 25. Question number 25. Here in the given question, a flexed beam is given, or compound beam or the composite beam, on which there is a moment, sagging moment is applied, and there are two material having the modulus EA and IA, which is the second moment of area about the axis, and the another material having modulus of elasticity EB and second moment of area about this axis. We have to find the radius of curvature R. As we know, the moment is taken by these two different material. So the total moment of resistance will be MA plus MB. We know a bending equation M by I equal to sigma by Y equal to E by R, where this is the moment of resistance, I is the second moment of area, or we usually say moment of inertia about that axis about which it is bending, and this Y is the distance from that axis at any point or at any location we can find the stress. E is the modulus of elasticity and R is the radius of curvature. Sigma is the normal stress due to the bending. From these equation, this and this we can equate, and we can say MA equal to EA IA by R. Similarly, MB will be EB IB by R. Now putting these equation into this equation, M equal to EA IA plus EB IB divided by R. As the beam is pleased, okay, so strain will remain same, and also the radius of curvature will be the same. As it is a composite beam, then it will, if it is bending like this, then both the material having the same radius of curvature, this material and also this material. So R remains constant, and we can find our radius for curvature EA IA plus EB IB by M. So this is the correct answer. Question number 44. Here in the given question, there is the composite shaft which is made up of the two material, one is B and the material A, which is subjected to a torque T. This is the side view of the shaft. This is a B material, this is A material. This is subjected to a torsion or the torque T. As the shaft is composite, then if it is subjected by any torque, the strain or the twist, angle of twist will remain same in the both the shaft. For example, let's say this and this. This is some imaginary line, and now we are applying the torque, then this line will shift to like this. The angle between these two lines, theta, will remain same for both the material. Means twist in B will be same equal to twist in A. But we know the torsional equation. T by J G theta by L equal to tau by R. Here T is the resisting torque, J is the polar moment of inertia or the area of the section, G is the shear modulus, and theta is the twist, angle of twist. L is the length of shaft, and tau is the shear stress, and R is the distance or the radius, or we can say radius. So in the parallel shaft case, this is a case of parallel shaft. Here the resisting torque or the torque is resisted by both the material. So the total torque which is resisted will be equal to TA, torque resisted by material A, and torque resisted by material B. We have to find the torsional stiffness for the composite shaft. Torsional stiffness is shown by or denoted by KT equal to T by theta. It is nothing but is the amount or the quantity of the torque required to produce a unit twist. So by using this equation, T by J equal to G theta by L. TA will be G. If the material is different, then the shear modulus will be different. Theta A upon L. Length for the both shaft is same. Similarly, TB equal to G theta B L, because length is same for the both the shaft. Now we put TA and TB in this equation. T equal to G A theta A L, and also J is will be there, JB JA plus theta B JB upon L. As we already see, theta A and theta will be same. We simply say it is a theta. Then T, we are taking common theta and dividing by theta. GA JA plus GB JB, and L is common. So this will be the torsional stiffness of the shaft, total shaft. This will be the right answer. Question number 46. This is very simple question. We know the Euler buckling formula or the Euler buckling load, pi square E I upon L E square, effective length. Pi is just a pi, and E is the modulus of elasticity or the Young modulus of the column, slender column. This formula is applicable for the slender column, in which the longitudinal or the, we can say, one dimension is very larger than these other two dimensions. L if D, L more D are known as slender column. So this Euler buckling formula is applicable for the slender column, and there are different cases. For example, hinge column. Then the effective length, which is this effective length, L equal to L for the hinge column. For the fixed and the free column, this is L, then effective length is 2 into L. And another case is in which one is hinged and another is fixed. This is a deflected shape. Now this is the actual column and this is the crippling load or the buckling load. Then in this case, if the length of the column is L, then equivalent length is equal to L by root 2 approximately. In the case of the fixed column, both the side is fixed and this is the load. If the length is L, then equivalent length will be L by 2. Now we have to put this equivalent length in this equation to find the crippling or the buckling load for different boundary condition case of the column. Question number 66. We have to find the torsional constant for a thin walled circular section. Let's say this is the circular section having thickness of T and its mean radius of R or small r. We have to find the torsional constant J for this section. We know that we have to find, we know that J, torsional constant for a closed thin walled section, is given by 4 A square ds by T. ds is the perimeter of that section, T is the thickness, A is the closed area of that section. So now putting the values, A is, we know that the circle pi by 4 d square or say 2 r square. Diameter, mean diameter will be 2r. Then we will get the area, which is nothing but pi r square, which is the area of a circle. And now this ds by T, what is this? This is the perimeter of that section. We know that the perimeter of a circle is 2 pi r and this is the thickness T. Now putting these values into this equation, J equal to 4 pi r square whole square divided by 2 pi r T. By solving this equation, we will get 2 pi r cube T. So torsional constant for this section is 2 pi. If r is small, let's say r cube T. This is the answer. Okay, now how this formula it came into picture, let's see. We know the torsional equation T by J equal to G theta by L equal to tau by R. T is the torsion, J is the torsional constant or the polar moment of inertia, G is the shear modulus, theta is the twist, L is the length, tau is the shear stress, and R is the radius of some circular shaft. And we know that for a closed thin walled section, the rate of twist, which is nothing but theta by L, is given by T by 4 A square area, closed area, and G is the shear modulus, and perimeter, summation of the perimeter divided by thickness. So by comparing these two equations, T by J equal to G theta by L. Now we are taking theta by L will be equal to T by J into G. By comparing these two equations, this and this, J will be equal to 4A square divided by ds by t. From here, this equation comes into the picture. Right answer is this, and this is for the concept building.